Mr. Aditya Jyoti Paul is the founder of CAR, Google Explore ML Facilitator, and Facebook AI Scholar. It's a great pleasure to have you with us here, Mr. Paul, and without any further delay, over to you.
All right. I'm Aditya Jyotipal. I'm the founder of Cognitive Applications Research Lab. Is my screen visible? All right. I am Aditya Jyotipal, the founder of Cognitive Applications Research Lab. I have worked in AI for about the past 2 years. These are some of the organizations I had the fortune of being associated with. To find out more about me, there would be some links at the end of my talk, so you can ask me any questions or connect with me after the workshop. So today's talk is about machine learning and specifically object classification. So let us first of all understand what is machine learning. I'm pretty sure all of you might have heard about machine learning in some way or the other. There are a lot of definitions of it, but the common understanding of it is that you feed the machine some input data and also the labels which are associated with the input data in supervised machine learning, and only the input data where the machine finds some patterns on its own in unsupervised machine learning. So the object classification which we would be doing today is supervised machine learning, and this is a clear demonstration of like the differences between supervised and unsupervised. On the left part of my screen, you can see some stop symbols and which also have labels associated with them. On the right side of my screen, you can see some figures or some symbols which have maybe a triangle as a border or an octagon as a border, etc. So the machine would probably be separating the first two images from unsupervised into one cluster and the other into another cluster. So that's about supervised and unsupervised machine learning. There's also something called semi-supervised machine learning. So what happens here is you have a lot of data, and semi-supervised is somewhat of a vaguer different class of machine learning in which probably you would be adding some labels on your own by hand and then training it or giving the machine some idea from human expertise, and then the machine would go on to use that level of expertise on unsupervised and then learn better intricacies of the data. Alright, so we would only be focusing on supervised machine learning today, where we have both the images, which are the stop signs here, and the labels. So in supervised machine learning, one of the tasks which you can do is classification. There are many tasks like regression, classification, style transfer, etc. So one of the tasks which we have is classification, and among classification we have something called binary classification. What binary classification is, it talks about differentiating between two simple classes of data, like people who have cancer and people who do not have cancer, people who are male and people who are female. This sort of a clear distinguish ability. When we give this impart this to a machine, it's called binary classification. We also have something called multi-class classification. What that means is when you are say seeing an object and you say that it can be a cat or a dog or a truck, and your options are say more than two, maybe thousands, 10,000s, millions, etc. So in our first demo, we would actually be using a neural network which was trained on such sort of a classification algorithm. And also we have something called multi-class, multi-label classification. When you see the second image on my screen here, this is an example of multi-label classification. See, if you obviously this is a cropped out picture from a larger image, but if you see this cropped out picture, what would you call it? Would you call it a lion, a wildlife, a mammal? Because it's all of the above. So if you just call it one of them, it won't be very appropriate. So we have something called top K classification, which is used for multi-class, multi-label classification. And here it's obviously a lion. And the second label is wildlife because it is an example of wildlife and the mammal as well. So I hope this clear distinguishing ability between multi-class and multi-label classification is clear. If you have any questions, you can post it in the YouTube live stream as well. I get to see them and I would answer them at the end of this workshop. So, one of the most popular ways about how we implement a classification algorithm is using neural networks. We could obviously use something called a rule-based approach as well, but the issue here is that maybe for binary classification, a rule-based approach would work. For example, if you were to distinguish between a square, a simple square on your screen, or a simple line on your screen, using a rule-based approach would be much more efficient and better than machine learning because the rules are simple. But now, even just if we're talking about cats, there are so many types of cats and so many types of dogs. Some breeds even look like one another. So it becomes very difficult for a machine learning engineer to write rules for all of these. And that person would actually have to write thousands or even more rules per class. And when you're processing thousands of rules across thousands of classes, that would lead to a worse performance than machine learning. So here we actually have to understand the differences between rule-based and machine learning. Rule-based approaches are suitable when you have a simple task at hand, when you have very less data, and machine learning is good when you have a lot of data and the task is more complicated than something which a simple rule-based approach can do. For example, if you were to alphabetize a list of song titles, it would be a rule-based approach. If you were to sort some words in a list, that would be a rule-based approach. But if you were given some pictures of cats and dogs and told to distinguish between them, that in that case, it would be more smarter to be using a machine learning based approach. And on screen, we have something called neural networks. In each of these layers, we have some weights which are getting trained. And I won't be actually going into how backpropagation works or what the math behind this machine learning is. That would be out of scope right now. But I assume that we'll actually see how to deploy an algorithm or a neural network which would be using transfer learning to distinguish between cats and dogs. I will also be talking a bit about transfer learning and about what it is, how we are going to use it, and use that in the first part of this demonstration. All right, so assume that you have thousands of pictures of cats and thousands of pictures of dogs. And what can we do as an engineer to solve this problem and distinguish them that these are cats and these are dogs? All right, imagine that we just have the pictures and no labels. It would be a clustering problem or an unsupervised problem. But in this case, the case which we are looking at, we also have the labels of all of these cats and dogs. So what we do is we take this picture and the labels and we take out some of that data and we keep it aside. That is called a testing data set. So for example, imagine we have 1000 pictures of cats and dogs which are mixed together. But in each picture, we just have either one cat or one dog. Now we take out say 900 of those images and use that for training, and for the other 100 we use that for testing. So we train our algorithm, we get some testing data, some accuracy metrics. We see that we are not reaching very good levels of accuracy because we trained on just 900 images. That was not enough on to teach our algorithm all the intricacies of all the cats and dogs in the world. It could also be that because of our limited data, we did not actually provide a proper or a wholesome representation of our classes to the machine learning algorithm. So what we often do is we take some algorithm which has been trained on millions or even billions of data points by some company like Google, OpenAI, or Microsoft who had the capability of training it on such huge data and such huge architectures. So here we see on the bottom left of my screen, we have something called source data. All right, this is the data which those companies use to train, and the source model is the architecture. The huge, enormous architectures which have hundreds or even like or close to 1,000 layers, and they have trained this the first to the source data and the source model. So they trained their source model and the source data, and maybe they were doing some multi-class, multi-label classification like image. So obviously they had thousands of labels. But our goal here is to just train an algorithm which can distinguish between cats and dogs very fast. So here what we are going to do is we are going to take their model, we are going to feed it our own data of our cats and dogs. We are going to train the last few layers of this neural network, and then we are going to remove the top layer, which, for example, let me go back to the previous slide. Here you see that in the last layer there are 10 output neurons. So if you're just classifying between a cat and a dog, you do not need 10 output neurons in the last layer. Just one output neuron with a sigmoid activation function would be enough. What we now do is we cut off the last layer, we keep the previous layers as is, we add the sigmoid neuron in the last layer, and we are good to go. We are also going to actually demonstrate how using transfer learning is actually a much faster and reliable way of doing machine learning. So I'll move to another screen right now. Here I have taken the liberty of running the code on my PC beforehand because otherwise it would take about 6 minutes and 6 minutes to train for the two batches of code on which I'll be training. Alright. So let us understand what transfer learning is or how we are going to apply it. We're firstly going to do two things, feature extraction and then fine tune. In feature extraction stage, that's the actual beauty of transfer learning. The features have already been extracted. The feature maps, for example, for edge detection in the previous layers of the neural network have already been extracted, and that is by the companies. And when we load those weights into a neural network, we already have those trained feature maps, and it can easily identify between cats and dogs using those maps. Let's see how we can actually use that in this live demo. So what we'll do is we'll import some basic libraries and we'll import TensorFlow. The data set which we are going to use for this cats versus dogs classification is there in TensorFlow datasets. It's called cats versus dogs. I'll be explaining the code as well as I go through. So here we see that we have extracted this or downloaded and extracted the dataset with tfds.load. The dataset name is cats versus dogs. It has been split into train, uh, validation, and testing. Don't be confused by the writing train colon 80% train and train here. All it means is that for your data set, the first 80% is for training, 80 to 90% is for validation, and the last 10%, 90% and above is for testing. With info means the metadata would be coming in as well. As supervised means we will be downloading the labels as well. So now it's unpacked into a tuple for raw train, raw validation, and raw testing. This is our raw data and the huge size images which we will be rescaling and doing some pre-processing on as we go. The metadata is the labels and some data about the data which we won't be using right now. So all right, let's see what the shapes and sizes are. We can see that we have uh, an encapsulation variable here, which has the shape of none comma none comma 3. So each image has 3 channels, and each image, obviously, what is an image? An image is a representation of the information in front of the lens of the camera. And how do we represent or how do we approximate what is in front of the lens of the camera? We take some numbers between 0 and 255 and place them on this. Imagine we have something like a cuboid in front of us, which has say 256 rows, 256 columns, and depth is 3. So on the first layer, which is say your R channel or your red channel, you have 256 cross 256, which is 65536 values, and each value can range between 0 and 255. And to represent a value between 0 and 255, we use the data type unsigned integer 8 because 2 to the power 8 is 256. Alright, so I hope this is clear, but if you want to ask any questions, feel free to ask that in the chat section or the YouTube comments. Uh, get label name. So here we are doing is we are using the metadata to extract the labels of the cats and dogs. So here we see that on my screen, you see that we have this text written above the picture, dog, and here we have another dog. All right. After this, we have something called format the data. So here we are defining our image size because we do not want our images, every single image, to have a random size. For example, see in these two images on my screen, one of them has a longer length, one of them has a longer width. But when you're training it to a machine learning model, what we'll do is we need a fixed size of an image because we will be running a fixed number of convolutions in the first layer itself. Or even if you do not have some convolutions, if you're using, say, deep neural network, we'll be flattening the image and then using. So we need to have a fixed input size. How do we do that? We rescale the image to 160 cross 160. So here we see that we have used TF.cast to cast the images to float 30. The first step, the casting is required because otherwise whenever you do the second step by 127, all the values would become almost all the values would become 0 or 1, which are integer values. The integer would only be between 0 and 1. Now you see that all the values in my image have been rescaled to a range of -1 to 1. So how do we calculate this range? The minimum value of an image would be 0. So you do 0 minus 1, which is -1 is your starting range, and your maximum value an image can have is 255. So if you do that calculation, 255 by 127.5 minus 1, you will get 1. So every image has now been converted to a scale or a range of -1 to +1. Why do we do this? Because it helps speed up our gradient descent steps in the next part of the algorithm. Then we're doing a simple resize. The shape is 160 cross 160. It's provided in as a tuple. And this format example, this is the complete pre-processing that we had. It's converting our images and returning it with a label as well. All right, so now that we have this function to format our examples, we have to format every single example that we have in our training, validation, and testing, which we see here. Again, we do not want to train sequentially on the data because it could so be that all the images, the starting of the data set are cats, and then we have all dogs. So if our algorithm sees only cats in the first few epochs, it won't learn anything. It will just understand that every image which comes in as an input is a cat, and then it will learn that every image which comes in as an input is a dog. So anyway, we are not going to take any risks. We are going to use a batch size and a shuffle buffer size. So a batch size is that for taking every step in gradient descent, it will take 32 steps inside. 30. It will. I'm sorry. It will read 32 data points or 32 images. A shuffle buffer size is it won't search for these 32 images in the complete data set that we have, but randomly pick these 1,000 data points in advance, and in parallel use randomly select 32 of that 1,000 data points, and that 1,000 data points will be changing across every epoch. So you see that we have created some data generators here: train batches, validation batches, and test batches. I'm sorry, we just created those batches, and now we will be seeing the shape. So this, in Python, the pass keyword means that we are not doing anything inside. But there is no easy way of actually seeing what's inside a batch without actually running that batch. So what we do is we read the batch, we do not do anything on the batch, and we just print its shape. Make sure that we are on the right track. So here we have 32 cross 160 cross 160 cross 3 because we read 32 images. So the first value is 32. We read an image with 160 rows and 160 columns because we rescaled it. And all the images are colored images, so they have three channels, RG and B. Okay. So now we have image shape defined as this tuple, and we are making a base model, which is based on MobileNet version 2, which is the pre-trained model. We have downloaded the data, the model weights as well. You see it here. This is the way you download a pre-trained model, or when you're using transfer learning. So I'm highlighting it on my screen here. And you have mentioned weights is equal to ImageNet, and we have not included the DOP. As I was mentioning, the top would be probably classifying thousands of classes. We do not need that. So we threw away the top and did not download it as well. Now we create these feature batches on the base model, and they have the shape of 32, 5, 5, 1280. We'll be having a clearer idea of where this shape is coming from as we go on. But for now, you can understand that we have each batch of size 5 cross 5. So now what we're going to do is we're going to freeze this convolutional base or the model which we just downloaded. We are not going to train it. We're going to set it completely to false, and we're going to see the shape of the architecture of what we just downloaded. Let me zoom out a bit because it's a huge model, obviously. All right, so we see that we had a total about 2.2 million parameters, and we are not training on any of those. Now we're going to add a classification head, which is just going to be a simple one neuron with a sigmoid layer. But before we get into that, we have to add a global average pooling layer to transform these the shape from 32 cross 5 cross 5 cross 1 1280, which we have here, to transform this shape to just ending with 1280, to 32 cross 1280. To know more about what global average pooling is, you can check out the TensorFlow Keras docs. But simply put, it will pick out each of those 5 cross 5 values and take the average of those. So imagine you have 5 rows, 5 columns, so 25 values, and you have 1280 number of these. So what we're going to do is we're going to transform that to just 1280. This transformation is done with global average pooling when you're using a convolutional neural network. We also have something called a prediction layer. This is a simple sigmoid which I was talking about. Now we define our complete model, which has the base model which we downloaded, which has the global average pooling layer which we just added, and a final prediction layer. Alright, so we set our base learning rate as 0.0001, which is I think not the default for RMS law. At least for Adam, the default is 0.001. At least you have to train and test with these uh, models. The best way to do this is see which one is performing better. You can use a larger learning rate like 0.01 or 0.03 for the first 1 or 2 epochs and then decrease it. You can use a decay factor here. For example, you can type it out like this: decay is equal to 0.01 or something. I'm sorry, 0.001. Decay has to be much lesser as it's a factor. Or else you could also use a callback in TensorFlow, which we won't be uh, demonstrating here, but you can use something called a callback. You can Google how to use callbacks in Keras. The callback is called reduce LR on plateau. So it will be going on with a larger learning rate as long as it can. But when it sees an epoch in which the validation loss is not decreasing anymore, then the callback would come into action and your learning rate would be decreased. So this is what our model looks like. We initially had this shape 5 cross 5 cross 1280. Using the global average pooling layer, we converted to none, 1280. So there are 1280 outputs in the last layer. And finally, in the output layer, we have just one neuron, which is it's called dense, but it's a simple it's a neuron which is connected to 1280 neurons in the previous layer. So it would be learning 1280 weights, and it would also be having one bias term. So it has one more weight to learn. That's the reason we have 1281 trainable parameters here. It's very important to understand where or how these shapes are coming from so that we can easily debug our models. There are two trainable variables, the global average pooling and the dense, but that's not very important to understand right now. This was just a sort of testing to understand that the code which I had written was right. And we see that we have about 45% accuracy without any training. That's because if you randomly classify between a cat and a dog, you have 50% chance, right, of getting it correct. So anything between 40 to 60 is, I guess, a good approximation. It shows that our training testing split has been done correctly as well. So we see that our initial loss is 1.03 and initial accuracy is 0.45. Now we'll start training. But I have already done this training, so we won't be doing this because it takes about 6 minutes to complete. We start from a validation accuracy of about 97, and at the end of the first epoch, so just at the end of first epoch, with the we're using transfer learning, we can get 97% accuracy, and at the end of the 10 epochs, it raises about 98.58. But can we do any better? Of course we can. So till now, we see that we have not actually trained the neural network in any way. We have just used the previous weights, and we have trained just the global average pooling layer and the sigmoid layer, which we wrote ourselves as well. Now what we're going to do is we are going to take that big neural network that we downloaded that has some weights, right? So we are going to take the last few layers of that big neural network and we are going to train those weights as well. Also, for this training which we have already done, without unfreezing the last few layers, we can see that these are the training and validation part. Yeah, all right. All right. So as we just discussed that we had this training and validation curves for training just the last layer which we had coded on our own. So these are the curves, and we see that the training has been going on pretty smoothly. There are no rough edges or anything. We can also add something like a batch norm and dropout. But if we use them, we would observe some discrepancies between training and validation curve because for batch norm and dropout, the the metrics the metrics would be better when you are testing it and worse when you're training it. The reason for this is both of these layers actually do not, how do I put this? The simplest way of putting it would be they are just turned off when you are testing it. But what actually happens is all of the dropout layer cells get activated in the last layer when training. So only say 80% of the data would be used and 20% of the data would be used for testing. So this would actually take a little while to explain. So I would skip over this. You can and should actually read the documentation for this from the Keras documentation. Now, coming back to the fine tuning, as I was saying, we are gonna train the last few layers of the big neural network which we just downloaded and change those weights which we downloaded. So how do we do this? First of all, we set the base model that trainable is true. So we set the entire thing as true, but obviously we cannot train the entire neural network. So what we'll do is we'll set the first 100 layers. So in Python, when you write colon fine tune at which is 100, the first 100 layers will be set to false. This trainable variable or the parameter here actually decides if a certain layer or a certain neuron would be trained or not. So this is basically it. We again compile the model and we see the summary. We now have 1281 plus this 1.8 million parameters in the first epoch as in this neural network to train. And training it does take some time. It takes about 8 minutes to train for 10 epochs. And we can see the result of the training. We started from 98.28 accuracy and we went on to 98.62 accuracy, and it can actually be improved even more. Once when I was running this, I reached 99% accuracy. No, I actually have another demonstration that would take about 10 minutes. Is that all right? All right. All right, so with this, we come to an end of the demonstration of transfer learning, and we'll be now seeing how to use layerwise feature activation maps. I have already run this code, but apparently this runtime has to be restarted. So if you have any questions for transfer learning, you can post that in the chat section. In another 10 minutes, I will be demonstrating how you can use this layerwise feature activation map as a tool to find out when to use or what your neural network is seeing in every single layer as it goes through training. We won't be implementing a very big neural network for this. This is a small neural network. We will be using a data set between horses and humans. Again, a simple classification task. You see that just like the previous time, we are dividing it into training, validation, and testing. Sorry, just training and testing. There is no validation in this one, and we have about 500 images of horses for training and 128 images of horses for testing and 527 and 128 for humans. And this is the neural network architecture on which we are going to train it on. You see that we have just three convolutional pooling layers, one flattening layer in which what a flattened layer does is it takes 25 of your neurons or say whatever, say you have 5 cross 5 images, so it will take those 25 neurons and it will sorry, not neurons, those pixels, and it will cast them into a single 1D vector, and then you put them to a dense layer as well. So this is our architecture. Where did I exactly lose the connectivity? Mm, all right, all right. So, all right.
Okay, I'm sorry about that. We had a connection issue. Aditya, you're back live. You can share your
All
screen,
right.
and your screen is being shared. You can
All right.
continue with your presentation.
So as we were discussing the power of this layer-wise feature activation map, what we did was I give a brief rundown over what part has been covered till now. I do not exactly know which part I lost the connectivity. Hence, so what we firstly did was we downloaded the dataset. We divided it into training and testing. There were 500 horses and 527 humans for training. Then we created the batches. This was the architecture which we had. The architecture comprised of three layers of convolutional and pooling layers, and then one flatten operation and one dense, and a final sigmoid for the distinguishing between the horse and the human. This is very similar to the previous demo, so I won't go into explaining why we are using sigmoid here. This is the final model summary that we had. We are training a model which has about 9.4 million parameters. And here we have compiled a model. Now we'll directly jump into this demonstration. Sure, sure. This is the final demonstration which has, we trained it on this images and we now uploaded four images of horses and four images of humans. So we see that the horse too here has been misclassified as a human, and we are trying to understand why the machine made this mistake. So this is see the first layer had 16 neurons, as you can see here in the model architecture. The next layer had 32, and even then we had again another layer with 64 and 64. So we see that in the first layer we have 16, then two layers with 32 and two layers with 64, the convolutional pooling layers. So you can actually zoom in on each of these pictures by opening them in a new tab. That will give you a better understanding of by seeing which parts of the image are getting lit up and which part of the image is not getting lit up. Let's look at another image here. Say we pick up human 4, which I remember was getting misclassified. 4. So let's look at the image. This was the image. Obviously, it's getting misclassified because it has so many real humans. But to get a clearer idea, you can see that what the neural network is looking at each particular iteration. So in the first layer itself, if you zoom in, we can see that some of the neurons have just found out some background noise, which is the hair portions and the hands of the images. It was actually trying to do some edge detection, but it ended up doing something very different for this image. And this sort of an impression actually goes towards the horse, as we will see in the later part of this neural network here. So this code is available on my GitHub repository on github.com/freakyphoenix/explainablecv under this name, layerwise feature activation map. Feel free to play around with this code, and I would take 1 minute to explain this code cell as well. So what we have done is we have found out the names of those layers here, and for every single layer, we are trying to put the previous layers inputs into this model, and we are going to extract the image, if the effect of the image after it has been passed through that layer, and we see that that's called a feature map, and we are going to display those feature maps in this grid which we are creating here. So this is pretty much plug and play. You can basically copy this code, change the shapes around, and you can use this for any particular neural network. And we can also do this for any random image from our testing data set. So here we see that we have random the choice, horse image files plus human image files, and you can see how it's getting classified. So this is the image which was randomly selected. This is a horse, and it's correctly predicted it's a horse. And you can see that what the neural network is looking at, each particular neuron in each layer is looking at as it moves through. So this is how we use layerwise feature activation maps. Now I'll get back to my presentation and quickly give a rundown of what else has been done in explainable computer vision in the last few years. So we had something called uncertainty maps, we had visual explanations, we had saliency maps. You can definitely look at all of these. The latest approaches have been on GradCam++, which is from IIT Madras, I think. You can see the differences between GradCam and GradCam++. Additionally, one problem was GradCam would give you only one single heat map, and GradCam++ is better at finding images which are small in the background as well. So some of the efforts have been post hoc versus anti hoc. Post hoc means which is done after the model has been trained. For example, the approach which you just displayed was post hoc. Model agnostic versus model dependent. So some approaches which work on some models and do not work on other models are called model dependent approaches, whereas model agnostic approaches work for all neural networks or approaches. Global versus local talks about whether it classifies it as the entire image or only a specific part, does it display heat map, etc. So this shows the research efforts which have been going on. So a brief rundown of the research efforts is that why we look for explainability is for better human trust, debugging, and legal compliance. We should always be able to explain who is responsible if an AI is going wrong, and human-based evaluation makes it much more easier and trustworthy. These are the resources for my slide. You can check it out. This would be put on YouTube as well, so you can get those links from there. All right. So with this, we come to an almost an end of my presentation, and I would love to take any questions right
All right, all right. So let's go to Q&A.
now. All right.
So the first question that we have is, what will happen in the first model if we give it the picture of a horse?
For the first model, what Does when was this question asked?
I think
Like
it's part of your. I think they were referring to your
second.
first demo,
Okay,
wherein
so
you
the
were
cats
comparing
versus dogs.
different breeds of dogs.
All right, I understand. So, if you give an image of a horse and a cats versus dogs in a cats versus dogs model, you would find a random output. You're not actually supposed to give an image of a horse or any other class which is not in your output for testing, because that would not make the output very meaningful. But in case you can also do this, so what you can do is you can have an output neuron for cat or dog, or you can also have something for an unknown class. So for everything else, like it can include a truck, a guy, a girl, and a horse, and everything. So if that neuron is the most powerful, it can display neither a cat nor a dog. So you have one neuron for a cat and dog, and one neuron for neither a cat and not a dog. I hope that answers this question.
Okay, I suppose so. Let's move on to the second one. Can you explain why a CNN is more preferable than ANN neural networks for object and image classifications?
Yes, this is a very, very good question. The Of course, what we can do is we can always take an image and we can completely flatten it and we can feed it into a neural network. But the problem with that approach is it loses this ability to learn some feature from one part of the image and maybe apply it to another part of the image. For example, let's say that we have a person's face in the top left corner of an image. Alright, and in our training, all the images were centered, so the person was in the center of the image. Now, if you crop it or if you move it to the top left, in testing, it will fail because the neural network has only learned that whenever there is a person's face in the center of the image, it's a human. If it's not there, it's not a human. But using these feature maps which are learned in CNNs, you get this spatial flexibility. So wherever your image is, it will be able to correctly extract the features and predict it correctly. Also, another reason why CNNs are better is because it gives you some computational. It's cheaper computationally compared to training a deep convolutional neural network for the same level of accuracy. Okay, so these are the 2 points.
Okay, so the last question is how do you perform feature scaling on learning convolutions?
For feature scaling and transfer learning, you have to actually go back and find out whichever architecture you are using, what statistics they use. All right. So whenever you are using ImageNet statistics, there are three values: uh, the mean, the standard, the mean variance and standard deviation, those values. So you have to download those values and you have to get those values and you have to apply that particular scaling which they did for training over your data set. So this is again a very good question. So for example, imagine you're gonna planning to use ImageNet and they have done some level of feature scaling for their training. Now you decide to do some other sort of feature scaling for your training. It won't work. It would give bad results in testing as well. So you have to download or find out over the internet what sort of scaling was done and exactly use that scaling for your training as well.
Okay, and the last question we have is if object recognition through CNNs is so powerful, why is reinforcement learning used more widely in self driving systems?
All right, this is an interesting question. I'll take it in two parts. The first part is asking about the power of CNNs. Actually, even in self-driving systems, we often use convolutional neural networks. The second part is why use reinforcement learning at all. The second part is actually see, a self-driving car's goal is not just to understand what is there in front of you. It's like say it detects that there is a truck there, it's a car there. That is not sufficient for it. It also has to develop some rules, like where is it going and why is it going. For example, in reinforcement learning, we develop rules to understand, like a car is coming at this speed at an intersection. So if it keeps moving at this velocity, after some time it will reach that point. So if I move at this speed, I would crash into it. So these are things which CNNs do not do. CNN will just detect the image. So reinforcement learning helps you to learn some of these rules without explicitly coding them in that sense. So that's the reason reinforcement learning is more popular for developing rules or for training self-driving car-based approaches.
All right, Aditya. Thank you for
All
joining us
right.
today. Thank you for sharing your
Uh,
knowledge.
Thank you for having me here. It
Yes.
was a great workshop. Thank you.
All right. All right. So with that, we wind up the session. Okay.
All right.
Okay. Thank you very much for joining us today.